We are now recording. Let me get the slideshow set up from the current slide. Okay. Okay. Now, 7.1, if you recall, Chapter 7 is techniques of integration. 7.1 was integration by parts. 7.2 was trigonometric integrals, okay? And, the different identities we use for that. 7.3 now is trigonometric substitutions, okay? 7.2 was integrals that had trig functions in them, and how do you go about integrating those, okay, using trig identities. These are functions that don't apparently always have trig functions in them, but the trig substitutions is how you solve them, okay? So that's the difference here. All right, and let me get my pen activated and also zoom in on this. And actually, before we do that, probably I should have done some other things. The next goal, trig substitutions, is to integrate functions involving one of these square root expressions. And I should have done this before I blew this up. Oh, I've got this. Okay. Okay. If you have any kind of a square root expression that has an a squared minus x squared, a x squared plus a squared, or that could be a squared plus x squared either, it doesn't matter on addition, or the square root of x squared minus a squared, okay? Any one of those three forms, if you have a numerator or denominator, probably the best way to go would be trig substitution, okay? Now, let me give you a little hint now. Here's how I remember these. Those good old Pythagorean identities. Okay? Can you tell me what one of them was? Yes? Right? Is equal to 1. So therefore, say sine squared would be 1 squared minus cosine squared. So this would work for either a sine or a cosine substitution. Okay? Can you give me another one of those Pythagorean identities? I'll say one. Tangent squared plus 1 equals secant squared. Tangent squared plus 1 squared equals secant squared. That's what I would use for one that has that in it. And change that around ever so slightly. Secant squared x minus 1 would be tangent squared. So this is secant squared minus 1 squared would be tangent squared. So you see, if you have any one of these three forms, probably going to be a trig substitution that is most likely to help. I can't guarantee every one it'll work, but at least some of them it should. Okay? So, those are the ones we're going to be considering. So let's start with, okay. We'll also consider this, and I'm going to leave this alone for right now. The square root of a squared plus I'm saying this wrong. The other one has squared in it. This one doesn't. Sorry. Okay. Let me start that over. Okay. ax squared plus bx plus c. Now, of course, you're familiar with that, right? Standard form for a quadratic expression or equation. Maybe not quadratic function, but pretty close. Okay? Now, what we'll do with something like that is complete the square, and then you'll have something that looks like one of the toppings. Okay? So, we have ways that we'll work with that as well. Okay? Now, let's take this first one right here, okay? If you had an expression like that, which of the trig substitutions do we say might work there? Okay, yeah. Cosine or sine. Now, you can use either one of them. The book happens to choose sine. Now, here's something that's a little different about this, okay? In these, before when we did substitutions, we let u be something inside, right? Yeah. Not doing it this way now. We see the form, and we say that looks like a sine or a cosine form, so therefore, let's assume that the, and it's doing the substitution sort of backwards, okay? We'll let x, rather than let u be something that refers to x, we're going to let x equal, and since you have an a here rather than a 1, then you put a times the, we're going to use sine theta, we'll go and do cosine theta the same. That's going to be our substitution, okay? Now, here's the things to consider. What's, of course, one thing we want to do? Then dx is equal to a cosine theta d theta. Perfect. But notice up here in that expression, you have an x squared. So we also need to do that. X squared would then be what'd you say? If this is x, a sine theta, what is x squared? A squared sine squared theta, right? By it? Okay. Now, let's plug in what we've got. A squared minus x squared would be a squared minus a squared sine squared theta, right? By it? Okay. And then what we might want to do there is factor out an a squared. That's why we put the a in there, because we knew we were going to do this. A squared times 1 minus sine squared theta. And guess what we've got there? Cosine squared theta. So this is a squared cosine squared theta. And guess what? That's what's inside the radical. So if you put that inside the radical, that becomes square root of a squared is a, sine square root of cosine squared is cosine theta. So look at that, okay? If you have, say, that in the denominator and do this substitution, and you have a dx on top, the dx has a cosine theta in it. Hey, look at that. It works out really, really nicely. And you can do the same thing for the others. What would be your suggestion for the x in the middle one there? No, not sine. Tangent. A tangent theta. And then you square it, and you do your derivatives and do that kind of stuff. And the last one, what would be your suggestion? Okay, it'd be a secant theta. There you have it, right there. It's pretty nifty.
So the first one we can use the cosine?
You could use cosine. The only reason they usually use sine, let x equal, well, let me just, what I'll do is just erase, okay? Okay, all right. So let's, instead of using sine, let's use cosine. A cosine theta. What would your dx be then? Except it'll be a minus. minus a sine theta. That's, I think, why they usually use sine, because the derivative is a plus rather than a minus. It doesn't matter. Your x squared would be a squared cosine squared theta. Cosine squared theta would then be, okay, plug that in here. Ooh, I left one. Sorry. Oops. Then your expression in the radical would be a squared minus a squared cosine squared theta. And that would be a squared times 1 minus cosine squared theta. And 1 minus cosine squared theta is sine squared theta. And you have a squared times sine squared, and that would be square root of that would be a sine theta. So yeah, it works just as well. The only difference is this produces a minus sign. So it's easy to drop the minus sign, so I mean, forget about it. So rather than do that, most of the time they do the other. It doesn't matter, okay? Completely up to you, okay? Now, here's a little drawback, though. Not too bad, but a little bit, okay? When you do this substitution, remember that we have to limit when you do that substitution, the theta here has got to be between negative pi halves and pi halves. Okay? That's when you do this substitution here. It doesn't matter which one. So, because you see the sine and cosine functions go on and on and on, you've got to make sure this stays. What is the reason they limit that? Mostly because it's periodic, so you want to just keep within one period. For a period of sine, it would be between minus pi halves and pi halves. Oh, wait. That's not a full period, is it? That's half a period. Oh, I'm sorry. Once we've done this, remember, we changed everything. We started with sine, and then this became cosine. And that's the reason we stay between minus pi halves and pi halves, because it's 1 to 1 between minus pi halves and pi halves. It starts repeating itself outside of that, so we stay within that. I'm sorry. I changed it from sine to cosine here, but I didn't change that. So let's do example 1. So I'm going to clear the stuff off of here. All right. Evaluate this integral. 1 over the square root of 1 minus x squared dx. How would you begin? Now, first, if you're thinking, let's just do a regular old substitution, that won't work, because if you say u is equal to 1 minus x squared, your du would be minus 2x dx. You don't have a minus 2x dx, so that won't work, okay? So you need something different, okay? Integration by parts is not going to do you any good at all. So really there's nothing else at this point except their suggestion of the trig substitution. So which trig substitution would you like to go with? We'll do it either one. Say again?
Can we use the same thing, like let x equal to sine?
Yes. Let x equal sine theta. Now notice there's no a here. A is 1, so 1 times sine theta. That's sorry. All right. Then, what's the next step? dx is equal to cosine theta d theta. Perfect. Okay? Now, we also want to do this, x equals sine theta, but what we have up there is an x squared. So what's your x squared? Is what? Sine squared theta. Okay? But you also have a 1 minus sine x squared, so that would be 1 minus x squared would equal 1 minus sine squared theta. And what is that? This, yeah, this board drives me nuts sometimes. It writes and disappears and stuff like that. It's 1 minus sine squared theta, which is cosine squared theta. And then the square root of that thing would be the square root of cosine squared theta, which would be cosine theta. Okay. So, let's plug in what we got now. Your dx here is, this is the integral of, the dx is cosine theta d theta, and your square root of 1 minus x squared would be square root of 1 minus sine squared, which would be square root of cosine squared, which would be cosine theta. Now, you could have written all that up there. I don't care where you write it. And what is this? 1 d theta. What's the integral of d theta? Antiderivative of d theta, or of 1 d theta. No, not x, theta. Theta. Plus c, right? Indefinite integral. But what is your theta? Remember, your x is sine theta, so guess what theta is? Yeah. I'm going to write it a different way. I'm going to put sine theta equal x. Therefore, how do you isolate the theta here? How? Not dividing. It's a function, so you do the inverse function. Okay? So this would then be theta is equal to inverse sine of x. Now, that's why you're limited to minus pi halves to pi halves. Remember, for your inverse functions, they have to be 1 to 1. And where is sine theta 1 to 1? From minus pi halves to pi halves. That's why you're limited to that.
Why we put cosine in the numerator?
In the denominator?
I know the denominator.
Oh, okay. The numerator was our dx, right? You could move this right up there. Yeah. And that was cosine theta d theta. And then your denominator was cosine theta. So that's it. So here's your answer is that integral would be inverse sine of x plus c. Okay? Let's see how they did. There it is, inverse sine of x plus c. I just couldn't see where they wrote the final answer. Okay, the thing that you see on the screen here is exactly what we did. Well, not exactly like we did it. I did them outside and then put them in. They put them in and then did the transformation. I started here and did the substitution. They put it under the radical. They put the radical here and the radical here and the radical there, and then they came out with it. So, same thing. Okay. All right. Does that make sense? Now, this one didn't need it, but sometimes, in fact, most of the time, I like to draw little pictures too. You probably have noticed that. As soon as you say x equals sine theta, okay, I would say draw a little right triangle. Okay, it doesn't have to be anything special. Put your theta here, either place you want to. Okay, if that's indeed theta, what is sine theta? You tell me, what's the definition for sine theta in terms of right triangles? Sine theta is defined to be what ratio? Did y'all ever do some old hen called another hen, or Sakatoa, or any of that kind of stuff? No? Okay. Here's how I remember. Sine is opposite over hypotenuse. Well, in that right triangle, the opposite is this side, yeah, that vertical line, okay? Well, guess what that is? That's x. This is 1. X over 1, okay? So you can draw your little triangle like that and do it. This problem didn't need it. The ones we're going to do from now on, probably it's going to be beneficial to do something like that, okay? And by the way, let me just show you this. What would be the side down here, the horizontal side then? If the opposite side is x, the adjacent side is 1, the hypotenuse is 1, what would the adjacent side be? Pythagorean theorem is it's the square root of 1 minus x squared. Is that what you said? Yeah. And isn't that what we've got in our denominator there? Okay, and then look at this. 1 over that, well, we don't need it in this case. That would be your secant of theta, even though that's not helpful in this problem. But you see, the picture and the things all work together really, really nicely. This one we didn't need it. We could work it all without even drawing a triangle at all. But the next one, I think it will be helpful. Okay? So let's go to example 2. Okay. What I'm going to do is clear that, and let's do example 2. Now evaluate this one. The integral of the square root of 1 minus x squared dx. And guess what? You're in the same boat you were before. There's no regular substitution you could do. If you let u be what's inside the radical, you got du being minus 2x dx, and there is no minus 2x dx. It's just a dx, so that won't be helpful. Integration by parts, I'm afraid, will just get worse and worse and worse, so that's going to be messy. So let's try and guess which substitution that is. It doesn't really matter, but let x equal sine theta. Okay, again, you don't need an a because a is 1. Okay, then, just like before, dx is equal to cosine theta d theta. Okay, and just like before, x squared is equal to sine squared theta. Now you can skip some of these steps if you want to, but I was just drawing them all in. 1 minus x squared would be 1 minus sine squared theta d theta, 1 squared theta, which is cosine squared theta. And then the square root of this is, square root of 1 minus x squared would be the square root of cosine squared theta, which is cosine theta. Okay? So now what our integral is what? Cosine theta from this, that's cosine theta. Your dx is cosine theta also, so that's cosine squared theta, d theta, and then you could go back and use your cosine squared thing that we did in the last section, remember? Okay. Or if you don't like remembering that one, okay, which is perfectly fine to use it, and I guess that's what they do. They go back and look that up. You can turn back just a couple of pages, and you can probably see, your book may have it in a different place, but it was our equation 4. I think it's your equation 4, but it may not be in the same place. And that would be x over 2, or in this case that would be theta over 2, plus 1/2 sine theta cosine theta plus c. But wait a minute, Houston, do we have a problem here? I don't know. Do we? We know what theta is. It's exactly the same thing we had before. If x is equal to sine theta, what does that tell you about theta? What would that tell you about theta? Inverse sine. Now you can also say arc sine. That's the other way to say arc sine or inverse sine of x. Okay, so that would be easy enough to do. Inverse sine of x over 2. Okay, if you're getting back to x, okay, that would be this, plus 1/2. Well, we know what sine theta is. What's that? It's x, okay? Now, do we know what cosine theta is? Okay. Yeah, that has to do with dx d theta, but we really don't want to write it as a differential equation. That's where the triangle comes into play. Remember, just like we did before, it lets that be theta, then this will be x over 1. Sine theta is opposite over hypotenuse. And then cosine theta would be adjacent over hypotenuse. And just like you said before, this would be the square root of 1 minus x squared, right? So cosine theta would be the square root of 1 minus x squared. Okay? And then you have your plus c. Okay? So again, that's where little pictures will help. Hopefully you see and interpret results there. Okay? Now, so they have 1/2. They put the 1/2 in front. I'll put it over 2. 1/2 inverse sine of theta plus 1/2 x times the square root of 1 minus x squared plus c. Just like we did. And you see, you use that same substitution here that we did there. Same one in example 1 and example 2. Just this is in the numerator, the other one's in the denominator. So this one would require you to use cosine squared. Or once you do that. Now the other form, remember, for this would be a sine 2 theta. Sine 2 thetas don't do well with the picture. Okay? So don't do that. Leave it in the 1/2 sine theta cosine. So there were 2 possible solutions there. Choose the one that makes the most sense for you. It's easiest to deal with. Okay. Now, any questions on that? All right. Here then is the summary of what we were just doing there. If you have an integral that involves the square root of any perfect square, and even if it's not a perfect square, if it's a minus x squared, all you do now is then let this be the square root of a times sine theta. You know, so it doesn't have to be a perfect square, but it's sure nice if it is. Okay, if that occurs in greater than 0, okay? Try this substitution, and once you do x equal a sine theta, then do x dx is equal to a cosine theta d theta, and then the square root of a squared minus x squared would be the square root of a squared minus a squared sine squared theta, which would be a times cosine theta. So that will, we've done it twice or 3 times. It'll do every time. So you can just do that. But if you forget it, just work it out. It all comes out pretty easily. Okay. Then the question is, how do you interpret your results sometimes? And then the triangles help. Now, sometimes they help with sines and cosines. Sometimes you don't need them. But in the next ones, I think we'll see that they, well, yeah, maybe or maybe not. We'll see. Let's do example 3. Okay. I hate to use that. So let's use this. Okay. Example 3. An integrand involving a squared minus x squared to the 3/2 power. Okay. So here's what we're asked to evaluate. The integral of x squared over 4 minus x squared to the 3/2 power. Then your dx. Now, there's a little part of me that says maybe a substitution will work, a regular substitution. Let u equal 4 minus x squared. But no, it won't, because the du would then be minus 2x dx, and you got an x squared dx. So that's not a particularly good one. In fact, we really have a pretty bad situation here. I don't think anything is going to work well. So let's go back to a trig substitution. What trig substitution might you use? X equal is what? Okay, it's 2 sine. Remember that a. This is a squared, 2 squared. Yeah, so it's 2 sine x, 2 theta. X equal 2 sine theta. Okay? Now, what's our next step? Second, dx is equal to 2 cosine theta d theta. Okay? Now, you might also want to do, since your x up here is not in terms of the x's, you're trying to get the theta, so, but neither one of these are just x's, they're x squared, so let's figure out what that is. X squared is equal to 4 sine squared theta. Okay, good. So we're going to use that. We also need to know what 4 minus x squared is. And what would that be? It's what? It's 4 minus 4 sine squared theta. It's 4 minus x squared. Huh? Okay. X squared is 4 sine squared theta, right? So 4 minus x squared would be 4 minus x squared, which is 4 sine squared theta. Now you factor it out, okay? Which would be what? Maybe you're doing it all in one step. What would that give you? Yeah, okay. It'd be 4 times 1 minus sine squared theta. And you are already going to the next step, which would be 4 times cosine squared theta. Is that what you were doing? It's fine if you want to skip these steps. No.
Can we subtract 4? Can we cancel?
No, because, okay. This 4 is by itself. This 4 is multiplied by sine squared theta. So you can't subtract. Those aren't like terms. One has a theta in it, one of them doesn't. One has a sine theta, the other doesn't. So you can't subtract things that aren't identical, okay? Or similar, I'll put it that way. They don't have to be identical, but similar. Okay, so that gives you 4 cosine squared theta. But we really wanted the square root of this thing. And the square root of that thing is the square root of that thing, which is the square root of that thing, which is the square root of this thing, which is 2 cosine theta. All right. Now I think we've got everything done. Let's go back and do our substitution. The integral of x squared. Well, what's our x squared? 4 sine squared theta. Your dx is also in the numerator. That is 2 cosine theta d theta. Okay? And your denominator is, okay, I probably shouldn't have done all that I did. Let's just leave that 4 minus x squared as 4 cosine squared theta, okay? So leave that as 4 cosine squared theta. That's what that is. But that's raised to the 3/2 power, right? I might have gotten a little carried away there. Okay. Now, when something is raised to the 3/2 power, what does that mean? To raise something to the 3/2 power. Okay, the over 2 means take the square root of this, and that means cube it. So you can either cube it to begin with and then take the square root. I don't usually recommend doing that. I like to take the square root first and see if I can simplify it, and then cube the result. So that's why the square root of this then was your 2 cosine theta, right? So that would be 2 cosine theta cubed. So this is, now let me pull out what I can, okay? In the numerator we have an 8, so I'm going to pull it out for now. And then the rest of the numerator is sine squared theta cosine theta d theta. Okay? Because I pulled out the constants. Our denominator is, as we already said, take the square root first. That would be 2 cosine theta, 2 cosine theta cubed. Okay? Well, I don't want to write an extra line, so I'm going to go back and change that ever so slightly to be 2 cubed times cosine theta cubed, or cosine cubed theta. Is that okay? Is that cheating? You're cubing the whole thing, so I'm going to cube the 2 and cube the cosine cubed, right? Cosine, right? All right. Now, what is 2 cubed? 8. So this and that go out. Okay? Out of there. And now what do we have? Well, we have a cosine theta up here and a cosine cubed down here. So that leaves me a cosine squared theta, right? But remind me, what is sine squared over cosine squared? Tangent squared. So that's the same as the integral of tangent squared theta d theta. All right? Hey, that looks familiar. Let's go back a couple of pages to that table at the end of 7.2. And what was the integral of tangent squared theta? You know, they don't list it there particularly. They just do tangent to the nth theta. They don't do a squared. Okay? So, I'm real tempted, sometimes I don't resist temptation well, to go to the very back of the book and look at those tables, because they have a little bit more things in those tables. And let's do your table of integrals. That isn't on the page number here. And we want those in trigonometric forms. And there's a tangent squared theta, number 36. You see it? And that's a tangent u minus u plus c. So that is O. A tangent theta minus theta plus c. Oh, but wait. Do we even have a clue of what tangent theta is? Let's go back to this and draw our little triangle. What's that triangle? Do a horizontal, a vertical, and then do an hypotenuse, right? Pick out a theta. I like that one. There's a theta. This tells me that if I divide both sides by 2, x over 2 is equal to sine theta, right? Right here. We did x equal 2 sine theta. So if you divide 2, that says x over 2 is equal to sine theta, right? So if that's my theta, x over 2 represents, x would be the vertical, the opposite side, and 2 would be the hypotenuse. Guess what that makes your horizontal side? Four, 2 squared or 4 minus x squared, right? Okay. Now, if we know that, what is tangent theta? X over, opposite over, over adjacent. Now, okay, I was sort of kidding before, but if y'all, you may not find them useful, you probably know all this anyway. But have you seen the little acrostics they do sometimes for sine, cosine, tangent? Have you ever seen those? Okay, let me just go through them quickly, okay? Let's do an angle here, just like we did. This is an angle. We're going to call this the opposite side, the adjacent side, and the hypotenuse, okay? Now, sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And tangent theta is equal to what? Opposite over adjacent, right? Now, I'll tell you my history of this. I never learned them. I just knew opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. To me, that was enough, okay? But when I was in grad school, I was rooming with an undergrad. We had an apartment we were sharing. And his senior year, he was taking trig. And I thought that was awfully late to be taking. He was an actuarial science major. And he needed trig before he could do calculus. And so he was taking trig. And I don't think it's original with him, but he came up with this. SOA, S-O-A, CAH, S-O-H, C-A-H-T-O-A. And he said, SOHCAHTOA. Okay? Have you ever heard that? Okay. To me, I can't tell the difference between SOH and CAH, which is the A and which is the O. So that wasn't helpful to me. I knew what they were. But then when I was teaching here, even my first or second term, we were back at Bessemer State Technical College. One of the students in the class, she sat right about there, I believe, she said, "Oh, I'd never heard this before. Some old hag caught another hag taking oats away." I thought, oh, that's clever. I don't really like hags. Another couple of terms later, when I was teaching it, another student said, "Oh no, I learned it. Some old hen caught another hen taking oats away." I like hens better than hags, so I go with that one, okay? But this is just a little thing to help you remember those relationships. But you probably already know, so don't worry about it. But I just thought if it was helpful, I'll throw it out there. So here we have what tangent theta is, and I think you just said it. What did you say? Tangent theta is equal to x over square root of 4 minus x squared. Okay, so our answer here would be tangent theta, which is x over the square root of 4 minus x squared, minus theta. We know what that is. I wrote it down somewhere here, I thought. No, I guess I didn't. But right here, we can do it from this equation here. Sine theta is equal to x over 2, remember? Okay, so theta would then be the inverse sine of x over 2. Okay, and then plus c. Okay, there we have our solution. So you see the little triangles will help interpret those other trig functions for you. Okay, so let's see how they did. Okay, wound up with this x over square root of 4 minus x squared, good, minus sine, inverse sine of x over 2, good, plus c. Got it? All right. Now, remember the second type of an expression that we used. That was and here's that triangle. Here, I'll blow it up for you. Oh, I didn't want that. No. I don't want to do that. Yuck. I think I'm going to have to start over. Sorry about this. I hit the wrong button. Okay. Is that where we are? Yeah. Okay. This I was trying to zoom in. What's that? What's that? Yeah, this is the next thing we're going to do. Remember, the first one was square root of a squared minus x squared. That's the sign, usually. You could use cosine, but you have a minus sign there, so we usually use sign. This was the second one, and what's the key for this one? Tangent, because tangent squared theta plus 1 is secant squared theta, or a squared tangent squared theta plus a squared would be a secant theta. Okay, so that is what we want for this one. So x equal a tangent theta, okay? And if you do that, let me go on and do it. If you choose this, whoa, goodness gracious, I forgot I have to change the color too. Okay. If you do x equal a tangent theta, then what we have here is x squared. What would x squared be? It's what? A squared tangent squared theta. And then what would x squared plus a squared be? A squared tangent squared theta plus a squared. And what can you do with that? Factor out an a squared. Okay. And that leaves you with a tangent squared theta plus 1. And that would be an a squared secant squared theta. Okay. And if you're taking the square root of that, then that would be a secant theta. Right? Okay. Now, also, if you're taking x equals that, what would your dx be equal to? No. If x is equal to a tangent theta, what's the derivative of tangent theta? Secant squared theta. And that's why they put that there. So you see, if you had a secant squared theta in the numerator, a secant in the denominator, you're going to lose some secants there. Okay? And the square root of x squared plus a squared, we just did that, is a secant theta. So yeah, we got them all done. Okay. Let's do example 4. So I'm going to clear this out of the way. And let's evaluate this integral. 1 over the square root of x squared plus 9. And by the way, it works just as well if it's 9 plus 8, x squared. It doesn't matter. Dx. Ooh, sorry about that. Now, what you reckon is going to be your, how are you going to approach it? Let x equal tangent, something times 3 times the tangent of theta. Then dx is equal to 3 times secant squared theta. D theta. Don't forget the d theta. We're not really interested too much in what x is. We're interested in what x squared is. So what's x squared? 9 tangent squared theta. But we're really even more interested in x squared plus 9. So x squared plus 9 would be 9 tangent squared theta plus 9, which you could factor out a 9, and that leaves you tangent squared theta plus 1, which is 9 times secant squared theta. But we're not really interested in just not x squared plus 9. You're interested in the square root of that. So the square root of that would be the square root of that, the square root of that, the square root of this, and that would be 3 secant theta. Very nice. Okay? So let's rewrite our integral with all that information we know. The numerator has just the dx, which is, I'm going to pull a 3 on the outside, secant squared theta d theta, right? That's your dx with the 3 on the outside. Okay? And your denominator is that square root of x squared plus 9 squared, which we found to be, here the denominator has a 3 in it too, so they go away, and it's just secant theta. And guess what happens here? The secant thetas go out, and that just leaves you the integral of secant theta d theta. And that is one we did last time, and I don't know if you remember what it is. If you don't, flip back a couple pages or go to the back of the book. See if we can find just a secant theta. I see a secant x. That's number 13 on a couple pages before, or if you go to the back of the book, it's there too as well. What do you see it is? Integral of secant theta is, oh yeah, you're in the back. We'll find it back there too then. If I can get my pages to work. Here we go. Differentiation, the trigonometric forms. Oh, don't tell me they don't even list secant theta. Actually, They put it in weird places. It's number 13 back there in the back of the book too, under basic forms. Why is it under trig forms? I don't know, but it's under basic forms, number 13. You see it? And what is it? Ln, absolute value, second, secant theta plus tangent theta, right? D plus C, right, exactly. All right, folks, we may have a little problem here, though. How do we know what secant theta is? I know what tangent theta is. I can figure that out from up here. What is tangent theta? I know, it's tangent theta. Right here.
Yeah, it's going to be x over 3.
Exactly. So this will be x over 3. I know that. We don't know what secant is, though, do we? So where would we go to look? Draw your little triangle. Very good. A horizontal, a vertical, and then a hypotenuse. Okay? Now, pick a theta, any theta. I like that one. So let that be theta. And we know that tangent theta is equal to x over 3. Tangent theta is equal to x over 3. So where are those things? Opposite. So this is your x. Yeah, that's your 3. The adjacent is the 3. So there you have it. Now, can you give me secant based on that? What is secant? Is what? Hypotenuse over adjacent. You got it right. Secant theta is equal to hypotenuse over adjacent. Why is that? It's 1 over cosine. And cosine was caught another hen. Okay, so yeah, it's secant is hypotenuse over adjacent. Wait, Houston, we have a problem. Do we know what the hypotenuse is? What? Huh? And what is it? The square root of 9 plus x squared, or x squared plus 9. There we have it right there. That was your hypotenuse. So this will then be the natural log of, and if we use the, like we did here, the principal square root, we don't need the absolute values anymore. Okay? I don't think. So that would be the square root of 9 plus x squared over 3, okay, plus x over 3. And I don't know if there's anything in the problem that says x has to be positive, but I've got to find it first. I've lost my page. Which is this example 4? Yeah. Okay. Yeah, they keep the absolute value bars there. Okay. Because that x could be negative. Now, before I put my plus c down, though, let's do a little bit of playing with this. That's the same as the log of absolute value, the square root of 9 plus x squared plus x over 3, because it's common denominator, you just add the numerators, right? Now, what is a property of logarithms when you have a quotient? The log of a quotient is the difference of the logs. The log of a product is the sum of the logs. The log of a quotient is the difference of the log. Y'all are too young to remember slide rules. That was the whole principle of slide rules. You could make division of long numbers, big, hairy numbers, easier by taking the logs and just subtracting the logs rather than dividing. So that's what we're doing. So this says the log of absolute value of 9 plus x squared plus x minus the log of 3. okay? And then you could do a plus c. That's no better than the previous, but that's how the book writes it, okay? Let me see if I can find it now. Here we have it. Wait, nope, here it is. And they list it both ways, log of that plus c, which is the log of square root of x. And they put the x squared in front. It doesn't matter. X squared plus 9 plus x minus log 3 plus c, which then is the log of why do they write the same? Oh. You know what they do at the end? Log 3 is just a number. So just add it to c and just makes it plus c. That's what they did. Because you don't really need a log 3 in there. You're just adding a constant to incorporate the log 3 in the constant. So that shortened it to that. That's the advantage of writing it. Log of a quotient is the difference of the log. That difference, just the denominator just becomes a constant. So it's plus c. Okay, good deal. Does that make sense? Okay, that is example 4. Okay, we're ready now to look at the next group of radicals. Oh, and by the way, where did that picture come from? I'm guessing in your text you had a 5 somewhere there. Is that right? Was your example 4 dealing with 5 rather than 3?
So different than the one that
Yeah.
I only got my example 4, you said?
Yeah. It was the integral of 1 over the square root of x squared plus 5? No. What is it?
It's like going more further. The example is
What's that?
the book is going more further chapters. The example is different than the new edition. I have a different example.
Okay. Okay. You want us to work that, or are you okay with the way that does it?
I just go with the way.
Okay, just this? Okay. But this slide must have referred to something else. It wasn't in our edition. It's in a previous one. So we're not going to do that. But really, it's not bad. I wanted to point this out. You do have that.
That's
Okay.
my
Example
example 3.
3? Ah, okay. It's your example 3. If you have something without a perfect square, let me pull this up so you can see. I mentioned it before, but I thought we were going to have one, but that was the old edition had one, not the new one. Maybe we'll still run into one. If you have something with a square root of x squared plus 5, and that's not a perfect square, then your substitution, again, it's a tangent because it's got the plus in there, but now this thing is square root of 5 rather than, see, before we had a 9 here and this became a 3 because 3 is the square root of 9. Well, even if that's not a perfect square, you can still put the square root of 5 there. And it works just as well. So what we did before is still good. It's just not a perfect square. Okay. Then the next thing, I hope, is going to be this one. Integrals involving this form. Okay. All right. Well, have a good weekend. We'll see you Monday. And yes, you got a test or two to be working on, so that's really going to make it fun, isn't it? Yes. All right. So here's your integrals involving x squared minus a squared. What's our trig substitution going to be? Secant. Because secant squared minus 1 is tangent squared. So that's going to be what we do here. So if your x equals a secant x, if that is a perfect square. If it's not a perfect square, that's going to be square root of a. Okay, doesn't matter. Okay? What would be your next step? Dx would be? Going to be the a, that's going to be there. A, what's the root of the secant? Secant theta tangent theta. Okay, strange one. Okay. Now, the square root of your x squared minus a squared, then, if you square that, you get a squared secant squared x. Then you subtract the a squared from that, you get a squared secant squared x minus a squared. Factor out a squared, you get a squared times 1, the secant squared minus 1. Secant squared minus 1 is tangent squared, and then the square root of that is a tangent x. A tangent theta. Okay? So, almost does the flip of what the other one did. The other one, if it was a tangent x, you wind up with a, this gives you secant squared in here, but you still get secant there. So, very similar. But just carry it through so you don't try to memorize the wrong thing. Okay? With this in mind, then let's see if we can evaluate the next integral. This is example 5. The integral of dx, this time they put the dx on top, times x squared times the square root of 4x squared minus 36. Oh wait, that doesn't look anything like we've done before, does it? Okay? But we can still play with it, can't we?
Yes.
What would you suggest we do? Second? I couldn't hear what you said.
We can do the same trick.
Okay. Before I did that, here's what I would do first. Well, first, if you did that, okay. Let me do this, okay? Let's play around with this 4x squared minus 36. Can't we simplify that a little bit? What would that be? Okay, that'll be 4 times x squared minus 9. Perfect. Okay, so that denominator then would be the square root of 4 times the square root of x squared minus 9. Don't you think? Okay, well that square root of 4 is 2. So now what we have is, this will be the integral of dx, and that would be a 2x squared times the square root of x squared minus 9. Okay? Now, that I'm a little more comfortable with. Because even if I don't like that 2 in there, I can pull that 2 out here. Get it completely out of the way. Now, I still haven't seen a form quite like that. And I almost guarantee you no regular substitution is going to work. No integration by parts is going to work. And no, it's not got trig powers in it, so not that, but the trig substitution will. What did you suggest? Let x equal secant. This will then be a 3, right? 3 secant theta. Then dx is equal to 3 secant theta tangent theta d theta. Whoa. Okay. Now let's go back up here and play around with my x squared would be 9 secant, I can't write, squared theta. And x squared minus 9 would be, subtract 9, and then you can factor out a 9, secant squared theta minus 1, but what's that? 9 times tangent squared theta. Okay, and the square root of all that would be 3 tangent theta. All right, and the book did it already. I just like to think through it to make sure I'm doing it right. Okay, you can jump right to there if you remember it. That's what they got, 3 times the tangent theta. All right, so let's rewrite what our integral is. The numerator was dx, and there's your dx. Okay, now first, the integral has a 1/2 out front, okay? Second? Yes, so take the 3 on the outside on top of the 2, and that will give us a secant theta tangent theta d theta. There's your numerator. Your denominator was an x squared. Well, x squared, remember way back we said if x is equal to 3 secant theta, x squared would be 9 secant squared theta. Okay? Well, let's take the 9 on the outside, and 9 and 3 will go into 9 3 times, so this will be just 2 times 3. That's times there, so don't forget. Let me just write it. That's going to be 6. So now we have a 1/6 out front. Okay? And then our integral, our radical, the square root of x squared minus 9, remember that we figured out was just 3 tangent theta. So pull another 3 on the outside. So that's now going to make it 1/18. And we have a tangent theta down there too, right? Now, the good news is the tangent thetas disappear. Right there. The one of the secant thetas disappear, but it leaves you a secant theta in the denominator. So let's write, if I've kept up with everything, that's a 1/18, right? Times the integral of 1/secant theta. What in the world is 1/secant theta? Yeah, that's cosine theta. Cosine theta d theta. I think I can do that. What's that? 1/18. What's the integral of cosine theta? Antiderivative? Second? No, it's a sine. Okay. The derivative of cosine is negative sine, but the integral of cosine is positive sine. Sine theta. Okay. And we'd have a plus c here. But we don't know what sine theta is, do we? Yes, let's go back to our original definition. Draw our little triangle. Okay, pick out a theta, there it is. And we have that secant theta is x/3. So what goes where? On the what? On the horizontal? No, on the hypotenuse? Okay, right. Let's go back and review this. Secant theta is equal to hypotenuse over adjacent. Yes, because it's reciprocal of the cosine. Cosine is adjacent. Okay. Your hypotenuse here, so secant theta will be that, and we know here secant theta is equal to x/3, right? So that means the hypotenuse is your x, and your 3 is your adjacent. But what we want to know is what is the sine of that angle theta? The square root of x squared minus 9. Right? So now we have 1/18 times, we have what the opposite side is, so that would be, the sine of that then would be the square root of x squared minus 9 over x. Right? Got it? Plus c. So I'm guessing they probably write it like this. The square root of x squared minus 9 over 18x plus c. Now they may not write it that way, but that's how I would write it. Square root of, yeah, that's how they do it. Look at that. They got it right. Good for them. Yeah.
How do you get the x squared, square root x squared minus 9 in the numerator?
How do you get that?
Yes.
Okay, your triangle here.
Yeah.
Did we say the secant of theta was
Oh,
x
yeah,
over
yeah.
3? So this side over here, I thought you told me was the square root of x squared minus 9. Right?
I see what
And
you
then
mean.
the sine of this angle is opposite over hypotenuse.
I see.
There you go. Okay, how are we doing on time?
I think it's time to go.
Okay, sorry we got started late today.
That's fine.
Huh?
It's 11:13.
11:30, and we get out of
13.
huh? 11:13. Oh, so we're only 3 minutes late. Okay, no extra charge. Okay, all right. So we'll start next time with square roots of general quadratic functions. Okay, I think that's where we're leaving off, and we'll pick up and go from there. Okay, homework exercises. I know you don't want to leave without some of those. We almost finished the section. I think you can do, it's hard for me to see this, either 1 or 3 or both. Any of the odds 5 through 9. Do 11 or 13 or both. And any of the odds 15 through 31. Okay? 33 is sort of an interesting little proof. You could try that one. And or 35. Okay? No. Hold off on 35. I think your proof will be 33 is the last one. We'll pick up the rest of those next time. All right, good deal. All right, then we will have a good weekend working all that calculus. That'll make it great weekend, won't it? Okay? All right. And we'll see you Monday. All right, I'll shut down the